We are welcoming today Mr. Milan Rapaić from Serbia. He will present a talk on seamlessly scalable self-stabilizing grids beyond Droop control network. Milan Rapaić comes from the Faculty of Technical Science, University of Novi Sad, Serbia, and he's involved into application of control theory and optimization, with particular emphasis on systems of infinite dimensions. He's member of the group appointed by the government of Serbia for establishing strategy of developing IA in earth-prone Serbia in the period of 2020 to 2025, and later action plan for implementing the strategy in the period of 2020-2023. He published more than 30 articles in SCI indexed journal papers, 3 books in Serbian, and also one international patent. Mr. Rapaić, the floor is yours.
Thank you. Thank you, everyone. Again, thank you for having me here. Since I more or less know most people present, I will skip the part where I introduce myself, and also it has already been done. I just want today to shortly discuss one of the ongoing projects, which I think is also interesting from a control theoretic perspective, and from the it's motivated by the need to change the approach to maybe primary and secondary control in distributed energy resources. So primary and secondary control of the power flows, of the frequency, and of the node voltages. So as a simple agenda, I'll try to speak higher. Lower or higher? Louder. Oh, okay, I'll try. So as a short agenda, I will try to explain the challenge, to formulate the problem in a formal manner that can be attacked by control theory, to propose a solution, and also to show some initial results, initial verification results, or some experiments or pre-experiments. So the challenge. So essentially, this is a conventional grid. This is the system that exists since the end of the 19th century. This is the grid that operates today, and its most prominent feature is that it is based on the fact that you want to produce the energy at places where it is abundant, and you want to move it to places where it is needed. It is actually the reason why electrical energy is so good, because you can move it easily. It is more or less the most easily movable form of energy. It can easily be transformed, it can easily be moved. This property of the grid has several consequences from control theoretic point of view. First, the entire system is essentially hierarchical. Not exactly centralized, but hierarchical. There is a strict separation of concerns in the conventional grid. Also, the system is I'd say divided very firmly into 3 domains: generation domain, transmission domain, and distribution domain. And the network is not the same, the rules are not the same, the problems are not the same in those 3 domains. Essentially, there is, for example, the transmission grid is highly interleaved, while distribution grid is radial. The way the grid lines are organized, the way that companies who feed us, depending on what their level they're operating. The fact is that this system is maybe not the best system for today. The reasons are partly environmental, partly political, but essentially this system, let's say there is a consensus that this system cannot remain the same in the future. There are several decisions by the European Union made towards the democratization of the grid, not only from the perspective of introducing more renewable resources. There is a recent decision that is strictly concerned about decoupling from dependence of the oil and different stuff coming from Russia in particular. So there is several axes, several lines of needs that require us to change the grid. And now, because we have to change it, there are several problems, but those problems are typically also opportunities. I tried to somehow make it clear on this slide what are the problems and what are the opportunities. One of the great properties of the classical distribution generator based on synchronous machines is that they have natural elasticity. If, for example, we have several synchronous machines powering a part of a grid, and we have a large consumer that is attached, this consumer has the potential that instantaneously it takes more energy than it is produced. This is not a problem if you have synchronous generators, because the lack of energy, the deficit of energy, will be introduced into the grid by taking the kinetic energy of the rotors of the machines. So the frequency will drop. This is enough. This will give enough time for the network to act, and so that the production is increased, so the power flow is balanced again, and everything works. But in microgrid setting, with the distributed resources, with solar panels, with wind turbines, you simply don't have that kinetical energy as a resource. So you need a battery. So the first point is that you need batteries in a modern grid in order for it to operate flexibly. Without batteries, you can have the situation which was non-existent in the conventional grid, that grid just collapses. Because if at one point there is no energy, simply you don't have the resource to take it. Now, this also, there is a counter problem, let's say, that the conventional power plants are slow. In order to increase production, you need time, and this time is not big. And I gave a couple of examples. For example, for a nuclear power station, typically it can change the ratio of production by 5% per minute. So if you need to increase it by 20%, you will need 4 minutes. Distributed energy resources like solar and wind, which connect to the grid through inverter, can do that more or less instantaneously. So if there is a capacity for production, you can have more or less instantaneous change. Unfortunately, also distributed resources tend to be volatile. If you have a set of PV panels, a cloud can reduce your energy production significantly, even if it is a nice day, no rain. But if the panel is in shade for any reason, your level of production is quite slow, and it's quite small, and we cannot predict this. The lack of predictability is also one of the problems. There are one big and several small companies in Novi Sad that work on prediction of consumption of electrical energy. And if you try to, let's say, to predict what happens on a city level or region level, it's completely doable. And there are very good algorithms to do it. But if you go down to the distribution level and try the same thing, it's almost impossible even in the conventional grid. When you introduce a big quantity of renewables, the problem becomes even bigger. So another problem with distributed generators is that they tend to be at various levels of the grid. So they tend to be also in the distribution level. This implies that the flow of energy is reversed compared to the conventional one. So the grid was designed so that the energy goes from the top, so from the bulk generators to the consumers. In the modern grid, this is not so. So you can have the reverse flow of energy, and the grid was simply not engineered for this. And there were big problems. For example, I think in Germany in 2019, they had negative price of the electrical energy. So if you had a PV panel and you put some energy into the grid, you had to pay for it, because at some points of the grid there were too much energy. So why is this a problem? It's a problem because voltages grow. So node voltages tend to grow. If you have too large voltage for some period of time, different bad things can happen. The equipment can malfunction and similar stuff. So essentially, this volatility can be two ways. not only that you can have not enough energy, you also can have too much energy, which you don't know what to do with it. The third important point from the perspective of this presentation is that in the conventional grid, as I said, everything was hierarchical and you had strict separation of concerns. So either you are a producer or you are a consumer, or sometimes maybe, not so often, but sometimes maybe you are a storage of energy. In the modern grid, you can be all three of these things in the same time. You can be a battery and electrical car in the same time. Essentially, you have much better operational freedom than before. And there are some things that are just facts that can affect both the classical and the modern grid. That is digitalization, aging infrastructure, which is a big problem, and increased power demands. Simply, we need more and more power all the time. Aging infrastructure is a particularly big example, a big problem from an economical point of view, because the grid was created at some point, and usually governments invested a lot of money in it. And now you need a lot of money to keep it going. And there is not so much public funds for this. And one of the idea of introducing prosumers is to make incentive for private individuals, not companies, but individuals, to give money for the grid. So to be able to earn money for the grid, so that they have incentive to put some of their own money to invest into the grid in a way. And so this talk essentially focuses on one small part on the modern grid, and that is the microgrid. So small part of the grid, which hopefully can operate semi-autonomously with respect to the other parts. My assumption in this talk is that this is a distribution level microgrid. So we can assume that these are houses which are somehow geographically close, that are connected to the main grid through the same transformer, let's say. They can operate as a single unit towards the rest of the grid, so the grid can see them as one connection point. In this case, they can, for example, trade with the grid through one connection point, or the grid can see them independently as independent individuals, units. It's the same, it's not a problem. So first question is, what do I have to have, what I need to have on the level of each individual house or unit in order for the microgrid to become a smart grid? Well, I need to have a smart inverter. And from our electronic point of view, let's say, I need to have a device that looks something like this. So on the left side, I have some kind of local consumption or some kind of local loads or some kind of local production. So here there can be strings of PV panels or some local wind turbine or something else, or common house utilities, whatever. All these are typically, well, if it is a wind turbine, it's not AC-DC converter, but AC-AC converter. But essentially, you have to have an energy converter that feeds all the energy to a single point. This single point is usually called a DC link, and in small inverters, it is just a battery of condensators. Sometimes it is a supercharger, depending on the size, but essentially it is a small battery. The aim of this battery is not to store the energy for later use, it's just a filter, a damper for frequency oscillations. Then you need to have a DC-AC converter, which will be able to produce energy in the appropriate form that you can feed it to the grid. Also, if you don't want to mess with the grid, you need to have grid filter. Usually these were LC filters. Now they are more typically LCL filters. And these LCL filters give you really nice waveforms on the distribution line side. So this is all this. So the lower part of the picture is relatively classic. This organization of the two inverters with a common DC link is sometimes called back-to-back configuration, because you have the source of energy here and source of energy here, and you can have a bidirectional flow. So in this way, these guys here can be producers or consumers, and the electronics remain the same, only the control of the two inverter changes. But if you want to make the unit autonomous, we also need a way to make it somehow smart. Typically, we need a microcontroller or a DSP processor to control the two inverters, and we also need a CPU to implement the trading part. So if we want that the grid unit becomes an agent that can buy and sell energy and participate in the market, it has to have some ability to have some intelligence, and typically you need a more powerful computer for that. So I just said CPU here. It's a computer of some kind. And also you have to be connected to the internet in order to be able to communicate with other similar agents. And so, together with colleagues from another department in Novi Sad, we proposed a project, and we are waiting the evaluation for the project to build such an agent. The lower part, the power electronic part, we already have built. We developed a device based on silicon carbide transistors, which can switch very fast, so that this filter can be relatively small and still have a very nice output. But actually, the idea is to develop the upper part. The project is called Grid Force. It's seamlessly scalable, self-stabilizing grid. So it's 4S. This is why it's called Grid Force. It is a play of words, Grid Force and Grid 4S. So the idea is to develop a control strategy which will be aware of peer-to-peer trading, and also to have a layer that has some kind of intelligent agent inside. Our idea was to use reinforcement learning in the upmost layer, and to use nonlinear control in the Grid Force S layer, which is the topic of the present presentation, and to use a conventional control for the current and voltage loops. Those are PI and PID controllers. So this is it. So essentially, the part which is here denoted as Grid Force unit is more or less conventional. So the novelty or interesting part is in the power electronic domain. The new parts are Grid Force control and Grid Force agent. Grid Force agent is non-existent at this point because we still haven't obtained funds to make it. But Grid Force control is the topic of this presentation. This is the paper we have in review at this moment. So the first point is to try to formulate the problem so that it can be solved by control theoretic means. In order to do so, I will imagine the grid to be a graph. So it's a graph. Each node of the graph is a unit. To each node of the graph, we associate a phasor. Phasor is voltage, amplitude, and angle, essentially, a complex number. The nodes are connected through interconnecting lines. Each line has associated impedance to it. Now, just to explain why is this completely okay. If you have one house, for example, it doesn't have two independent connections with the rest of the world. It has a point of common coupling where it connects to the distribution grid, and here it is the same. Although, for example, there are three lines coming to node 3. Node 3 has one phasor. It means it has one point of common coupling with the rest of the world. So the three lines are drawn here just to be obvious what is happening. That it has direct electrical link with three other units, but essentially this link is created through point of common coupling. So one phasor per agent. Also, it is mathematically easier to work with admittances than impedances. Why? Because in this case, two nodes that are not connected have zero weight between them and not infinite weight between them, so it's more convenient. This is why I use Y's, not Z's. So if I concentrate on a pair of nodes, so they have each of them has two phasors, and this is a matter of simple calculation that if the grid is in the synchronous regime, so both oscillate at the same frequency, P and Q, these expressions are expressions for the exchange active and reactive power. Well, the term exchanged is not maybe the best one, because each of them is, let's say, emitting a certain amount of power. Some of that power is lost, but some of that is exchanged. Typically, the lines in modern grid are mostly inductive. So you can, in a conventional grid, you can describe all lines as inductive lines. It's not so on the distribution level, and it's not so in modern microgrids. So sometimes the ratio between the resistance and reactance is not so small. So here it's assumed that it is an arbitrary admittance. So no approximation here. We see that the amount of exchange energy depends on the voltage levels and on the voltage angle. And normally in the IC grid, the exchange of voltage, the exchange of power is achieved by adjusting angles. So the voltages are more or less the same, but the angles of phasors adjust to a certain difference, and the rate of power exchange depends on that difference. So for us, this is then the overall model of the grid. This is what we need to control. We have that each node is described by this pair of first-order equations. Very simple. We can directly control the voltage, and we can directly control the angle. The reason that we can do that is that we have inverters, which are power electronic devices. We can program the voltage and program the angle. The nonlinear part and the tricky part here comes not from the dynamics, but from the equations that describe the exchange of power. So if we want to control the exchange of power, that part becomes problematic. So it's, for me, it was quite a particular model when I saw it first, because I'm used to seeing bad things here. But here the model seems trivial, but actually the target is here non-trivial. And so if we then focus back on one node, we may assume that this one node has agreed to exchange certain amount of active power with other nodes. The sum of that power is the reference output of these nodes. For example, I may promise 10 kilowatts per each hour to one neighbor, 5 kilowatts per each hour to some other neighbor if I maybe have a lot of production facilities. So I know that each hour I have to produce 15 kilowatts, in addition to my personal consumption, if there is some. So how would we? So what is the goal of the talk essentially? The goal is to propose a novel control framework that will be suitable for this peer-to-peer context, and to demonstrate that the proposed algorithm can guarantee that your voltages and your frequencies will never deviate from predefined bounds. So that you can, in advance, say, I want to guarantee that at no particular time instance, the frequency will go more than 1% above nominal, or drop more than 1% below nominal, and that the voltages will be in, let's say, plus minus 2% of the nominal voltage. So this is the idea. So, and also, and this is very important for later, is that to show that we can adjust this framework to different grid codes. Grid codes are the rules that the grid operators impose. Let's say, what kind of rules? Let's say that I promise 15 kilowatts each hour, but I managed to give you 10. Somebody has to pay I have to pay for not fulfilling my agreement. So this costs some money. The proposed framework is such that I can adjust my preferences. I can say, okay, in which cases I can agree with myself that I will not give the amount of power I promised. So just quickly, what would be the classical approach to this? The conventional grid has a three-layer control architecture. We have primary, secondary, and tertiary control. Primary control is typically implemented on the level of individual generator, and it's called a Droop characteristic. It is a rule of thumb saying that if you have an excess of, synchronous generators do that by themselves. Essentially, if you have an excess active power, you should increase frequency. If you have less active power than you need, you should decrease frequency. And similar relation exists between reactive power and voltage. Too much reactive power will increase the voltage, too little will decrease the voltage. Primary control manages to set the frequency to be equal amongst all nodes, although this frequency will not be 50 Hertz. It will typically be less than 50 Hertz if you don't have enough power. And then secondary control comes and activates the reserves, essentially increases the production rate of power plants so that the frequency is returned to the nominal value. Tertiary control actually deals with trading, optimization, operational aspects, so it is above. Primary control is a Droop controller, and the secondary control is typically a PI or PID control that operates on a level on one control unit. Just for reference, this is the Droop control. You have a curve that specifies how much the frequency changes depending on how much active power you have, less or more than you want to have. So, and this is how secondary control essentially works. For us, for me, it's important just as a reference. In secondary control, you have a PI that directly affects the active power set point of each generator, and this PI works based on an error. An error is created as a combination of two factors. One is the error in the agreed exchange rate between different areas, plus certain factor times the error or the difference of the actual and the nominal frequency. So this PI will try to get two things right: to return the frequency to normal and to achieve the desired exchange of active powers between different control areas. Only in the nominal, in the conventional case, this control area is not one house, but maybe several cities. Essentially, control area is linked to one bulk generator, so it can be really big. So now I will try to explain what we try to do. First, we try to represent each prosumer as an agent with its own goals. This goal-based multi-agent approach is used very effectively in robotics, for example, especially in mobile robotics. You have multiple entities that move through some space, and you want that each of them achieves their own goal without communication. If you remember, maybe 5 or 6 years ago, it was very popular on YouTube to see videos of a bunch of drones that are flying inside of a room, making some kind of configuration or balancing a glass. Usually, what happened at that point is that there was a central controller that communicated with all the drones and sent them information what to do. This is why it was for several years, it was impossible for you to find such a video of drones flying outside. Now they did it, so that each drone is decentralized in the sense, decides for its own. But for a long period of time, these kinds of demonstrations were with centralized controller that communicates to each drone what to do. So the idea with goal-based approach is that each agent, in our case, each prosumer, decide on its own what to do, without communicating with other prosumers, and to define the manner in which they are doing what they are doing, so that the whole system is happy. So the whole system operates in a good way. So assume this. Assume that just for presentation purposes, that this is a certain object. This is a movable entity that wants to go to the cross. So the target is the green cross. I want to make a goal function which will explain how the blue entity, how happy is it with its current state, or how unhappy. In engineering, we always define unhappy. We define error. So what is the measure of unhappiness of this drone? We can say that it is a quadratic function centered about that x. The farther I am from x, I'm more unhappy. And if I want to design a control strategy, I can say, give me a control that will reduce the level of unhappiness. So usually it moves in the direction of the gradient, negative gradient of the unhappiness function. And this negative gradient would be toward the x. But imagine that you have two other objects in the middle. So I would like to come to the X, but I would not like to collide with some of these objects. So essentially, my level of unhappiness has two parts. One is how close I am to the goal, and the other part is how measures the dangers of collision. Now, one naive approach would be here to define the goal function in the following way. I have a quadratic which is concave, that is centered around my goal, and then have another convex quadratics that are centered around the obstacles. And I make one goal function. The problem with this approach is that essentially, if I really, really want to reach the goal, I will try to go through the obstacle, which is impossible. So the trick that was introduced by Lightman, I think, in the middle of the 20th century, is to define the parts of the goal that define my desire to be away from obstacles as going to infinity when I reach the obstacle. This means that if I am very, very close to the obstacle, my measure of unhappiness will be incredibly high. So gradient towards, with respect to this will tend to drive me away from the obstacle and then to the goal. And so in this particular case, let's see something like this, the algorithm will drive me like this. So I will first move toward the goal, but I will go around the obstacle. And this works even if there are, regardless of the number of objects, regardless if the obstacles are moving or stationary, assuming that everybody attempts to avoid each other, they will not collide. You can prove mathematically that they will not collide, even if there is no communication among them. So only each of them can measure where the others are. And so idea was to try to apply this approach to the microgrid setting. So we wanted to have no communication and to guarantee no collision. Collision here is not with other agents. Collision here is that we reach the limits of frequency and voltage. So this is what we try to avoid. And so this is the proposed solution. So that we take each presumer and define its local goal function. This local goal function has two components. The first one defines that he would like, or it would like, to have zero error of exchange energy. So if he agreed on 15 kilowatts, he wants to give 15 kilowatts each hour. And the other function, other part, this is the beta function, tells you how unhappy he is with his current node voltage. And beta is that function on the right. So beta is a function that goes to infinity for finite values of error. And these gray parts of beta are not important. The convex one is important. So we want to control in such a way that we go in the direction of the gradient of the local goal function. This means that once the voltage becomes close to the boundary, the inverter will use all its resources to stabilize the voltage. It will say, I don't have the resources to trade, so I will not trade. They're keeping the grid live, keeping me inside of the grid in the predefined operational regime is more important than trading. Trading is secondary. So we all earn money by trading, but if there is no grid, then we cannot trade. So keeping the grid alive is primary. If my voltage goes to the limit, and I will give all my resources to keep myself within the limit. And if the voltage is near the nominal, then okay, my error is completely tied to the error which I make in exchange of power. And after some calculations, you get the control law, which is like this. And we were really happy to get this. Why? Because all the quantities here are local, they don't require communication, and are easily accessible for measurement. So in order, the expression looks long, but essentially it's simple. You have to know what's your current voltage, what's your current power output, and the only two things that you need to estimate is your total equivalent conductance and total equivalent susceptance, but your. So you don't care what happens on the other side of the grid. You just need to know the sum of the lines that come that are connected directly to you. And there is a way to estimate this. You don't have to measure, you can estimate it. This eta function serves to guarantee that the frequency will never deviate from more than a certain amount of percentage from the nominal frequency. So essentially we hard-coded that. And we were able to prove, similar in that case, that if everybody behaves in this way, you can guarantee that the network will operate in the nominal conditions. So no voltage will go above the desired one, and the frequency will obviously remain in the range. And so the rest of the presentation is mostly based on how we try to persuade the power engineers that this is a valid control strategy compared to the Droop. First, it achieves power sharing in steady state. For power engineers, this is really important. So we can tune so what is power sharing? In essence, if I promise to sell you 15 kilowatts and you want to buy 15 kilowatts each hour, I cannot send you 15 kilowatts because some of this will be lost on lines. There will be losses. So I can send you maybe 15.1 and you can maybe receive 14.9, but we have both to agree that there is a certain discrepancy. Droop control has a very good property that the amount of discrepancy that each unit is receiving is proportional to its nominal power. So strong units will contribute more to the losses than the small one. We can achieve the same behavior or similar behavior in this strategy. And also, we tested in several standard grid. This is IEEE 13 test grid. These tests show what is the actual exchange power depending on the agreed amount of power. We see that essentially the differences are below 1% of the nominal power rate. We did the same on something that's called IEEE 123. It is a standard grid with 123 nodes. Obviously, it was difficult here to show for every node, but you can see that the errors are in the level of few percentages, which we consider to be satisfactory. For us, the control engineers, it was more interesting to see how the dynamics is behaving. So at this point, we are in the process of building a laboratory setup. At this point, all the tests are on the simulations and using hardware-in-the-loop simulations, using the Hill devices from. So we use because simulations last for long times, we use in the dynamic part just four unit network. And I don't want to lose too many time on this. We tested various things. A connection of a certain unit, disconnection, black start, transition to islanded mode, recuperation from the islanded mode. In most cases, when you introduce dynamics, the grid behaves actually better than when you have this crude model with just phasors. The reason is that the grid filters dump everything. So grid filters act as dampers, and dynamically the system is more stable than without them. Because this paper is still in review, in one of the review phases, one of the reviewers, for example, complained on that strong bump of the frequency, which you see in the upper 4 plots, the central one. It is an abrupt 2% jump in the frequency. This is not an actual jump, because if you see the actual waveforms of voltages, you cannot see that. This is because this bump happens in a really, really short period of time, It is a mathematical thing, not a physical thing. So just to finish, these are. I think it's pointless to explain each and every one of these figures. I just wanted to show that different quantities behave relatively nicely in this way. What we still didn't do, we didn't perform small signal analysis regarding stability. And I think that once we do that, we will not have these oscillations during the transient regimes. Simply that the transient should be damped better. But essentially, relatively, we can change operational conditions relatively fast, and in less than a couple of seconds, it adapts to everything. So, thank you very much for today. Also.
So bold.
Thank you very much. Maybe you can. We have time to pose short question at a time.
Yeah, maybe I have one. So I'm sorry, but I didn't understand all. But I think you try to explain that with a local control law,
yep,
it's possible, in fact, to obtain something that maybe is not optimal, but which works for a complete grid, in fact.
Yeah.
In a grid energy system.
Yeah.
It's okay.
Yes. If you optimal control for people who do this, and I'm not one of those people, but Dusan Stepanovic, I mentioned him in my first talk, my colleague from America that I worked with for maybe two years, he does only this. They hate optimal control in a sense. Not hate it, but they dislike it because he showed me a couple of situations, for example, this one. What is the optimal way to come from here to here? This is not this one. If you try to develop an optimal controller, it will do this, and then it will do this. Sorry.
Yeah.
And then it will do this. And the behavior here, you essentially enter a sliding mode. You enter a switching behavior in which an agent is entering inside, running away, entering inside, running away. The Lightman proposed this mechanism with these Lyapunov-like functions. They're not Lyapunov functions in the sense that they are not used to prove small signal stability or even global stability. They're just used to prove boundedness. So you say that a system will be, if something bad happens, this function should become unbounded, and you define control strategy that keep it bounded. And this is this idea. And you can manage to have a local information and completely distributed, decentralized, distributed control law, which achieves global stability or global boundaries. That certain global goals are achieved, although the nodes are not discussing amongst themselves. I mean, I can actually prove it, but
the constraints to satisfy the constraints and the specifications of the whole network. Even if you distribute control and so on, I guess that there may be some limits to the ability to achieve all the requirements at the grid scale. I don't know today, but it would depend on whether some nodes have a lot of power compared to neighbors or to some other grid characteristics. Discuss this point about what can contribute to help satisfying all the requirements and what could create troubles.
Yeah, understand. At the beginning, I said that I am assuming that the grid I'm talking about is a microgrid below a one transformer. So what I just explained works in a small portion of a distributed grid. If I would try to scale it up to the entire network, I'm quite sure that it would not work, mostly because the system is too complex. And for example, if I would scale it just to the whole network, it could be possible in principle that your house and my house, your house being in Bordeaux, mine in Serbia, that we agree that I will send you 1 kilowatt of energy. And how will I do that? I mean, I can feed this energy into my surrounding. And so at some point, you will take the same amount of energy from your surrounding. But essentially, this energy will have to, okay, the entire European microgrid is connected, but it's not so easy to push energy without intermediary. So I do not know the way how to scale this to the level of the whole grid. But maybe, I'm not sure, is it really necessary? So the idea here is that this is an approach that works locally in a community, which is interconnected in such a way that we can trade more or less freely. And what we can do, is make this, again, hierarchical, saying that this is my microgrid. So this guy is, let's say, trading with this. But somebody outside says, wait, I need some energy. And then we all are connected to the main grid here, let's say. So that we as a community send certain amount of power. And so that then we have interconnected communities, not individual entities. So again, we make a hierarchy of problems. But for sure, you are completely right. There are lots of, the grid is a complex system. It is not possible to show it as a simple graph of everybody is connected with everybody else in a way that is more global. Or maybe it is, but I don't know how.
Yeah, you showed us a slide with the Droop control.
Yeah.
I didn't understand very well. I don't know if it was the French word for Droop control.
It is essentially a P controller. So a French word for a Droop controller is a proportional controller.
Just proportional.
Yes, it is. And then the name of Droop is used in power engineering. I don't know why. I thought initially that it is drop because it drops, but they told me no, it's Droop. So there are two options. One, everybody in Serbia in power engineering says Droop instead of drop. And the other is that there is some meaning, jokes aside, in every paper in electrical engineering, this is called Droop.
Is it a mix of drop and loop?
I don't know, maybe. I can search after, but essentially it's a P controller. It's a P controller with a fixed offset. The formula would be like this because you can directly control the frequency. It says the difference between the nominal frequency and the actual frequency is proportional to the difference between the current and the desired power. It's just a P controller. But they like this picture very much.
So they use just the P controller? And
they use P controller.
Any integral action there?
No, because it is here.
Because it's there.
It's there. So in the three levels of control work synchronously, I'd say.
Yeah.
You have a primary, secondary, and that's it. And the integral action is on the secondary level. And so even I can implement this PI part in this scheme I proposed, because even this scheme achieves very good exchange of energy, but the frequency is not 50 hertz. It is 49.6, let's say. So, but you need to have a grid that works on 50 or 60 hertz. So you need an additional PI controller, essentially a secondary controller, which will now works only on this. It doesn't need to work on this for two reasons. First, it is not guaranteed that we have enough power to satisfy all the agreements. And secondly, because this primary control already managed that delta P is pretty good. So we essentially ensure that the frequency is 50 hertz.
I'm curious about the transportation, the type of transportation of the current. it's DC or AC, and if there is an influence on your microgrids?
Is there a difference? If there is
Difference.
if I have a DC microgrid,
Yeah.
what will change? Only the fact that only the fact that here there is no equation number 2. So no here. So you can remain. You have the same goal function. It depends on the difference between desired and achieved power exchange, and you have this term that guarantees that the voltages will be in good range. The difference is more physical because in DC microgrids you achieve power exchange by changing voltages. So you have to have nodes, you have to have different voltages in order for the power to flow. In AC microgrids, you don't have to do it. Every node has the same voltage, but the angles are different. So the power goes is moved from one node to another due to angle difference. And in DC microgrids, you have to have voltage difference, but this will happen more or less automatically with this kind of control. One of the reasons why this is, in my opinion, and I'm completely unrelated to this, so my opinion matters more or less. I mean, in my is because the following fact: Droop is based on the fact that there is a rule of thumb that the change of frequency is related to active power and change of voltages is related to reactive power. And this is true only if you have complete decoupling of the two power axes. And this happens only if the line is inductive. Inductive. If the line is not inductive, the two are mixed, and Droop is no longer effective. And there are many attempts to fix it by, for example, changing the axis, transforming the measurements, and so. So what I like in this approach is that this is done automatically. So essentially, the approach takes into consideration this automatically. Now, as I said before, since this is the approach we are just proposing, I'm, as always, in love with my own approach. After 1 or 2 years, I will probably have a bunch of stuff that I say that don't work, but at this particular moment in time, I'm very happy with it. So.
With this kind of microgrid that you can manage separately, there is a problem of the whole grid of the country. Can the microgrid still work independently for a small amount of time? There is an explosion.
Yeah. If you have a microgrid that has enough internal power in order to satisfy the basic needs of those participating, such a microgrid can operate indefinitely without the main grid. It's called the islanded operation. So it essentially cuts itself from the rest of the grid and operates independently. The problem is that you usually don't have enough power. If you don't have enough power, then you don't have enough power. There is no amount of control that can fix this. But at present, even if you have enough power, let's say you have 3 houses that have enough power, you cannot disconnect yourself from the main grid. Why? Because the 3 houses are not able to create the grid among themselves that is operational, are not able to create a common frequency to maintain voltages. So you need the main grid in order to make an environment in which you will produce power. Approaches like this have that power that they create the grid on themselves. So if the grid is non-existent, they will create one and then start to exchange power, if they have it. If they don't have the power, then they don't have the grid. So essentially, this can work without a dispatcher. So even if you cut the main grid, the units will autonomously form a grid.
Is there no other questions? No more? So once again, thank you very much.
Thank you.